Okay, I want you to imagine, just for a second, that you wake up completely blindfolded, right in the middle of a massive, complex maze. You've got zero idea which way you're facing, you don't know where the walls are, and there's absolutely no immediate way to figure out your exact coordinates. So, how on earth do you find your way out? I mean, it sounds like an absolute nightmare for a human, right? Well, believe it or not, this exact scenario is what artificial intelligence faces every single day when it's operating in these foggy environments where information is incredibly scarce or just entirely missing. Welcome to This Explainer. Today, we are exploring a truly fascinating concept that literally allows machines to function in the dark. It's called navigating the belief state space. So, what happens if an AI really is completely blind? Normally, when we think about a robot or a piece of software navigating through a space, we immediately think about GPS, right? We picture that little blue dot on a map on our phones. The agent represents its position as the single, absolute, fixed physical point. But when an AI completely lacks information about its current environment, well, that single point model just completely breaks down. If it literally doesn't know where it is, it obviously can no longer just track a single dot. It has to completely, fundamentally rethink the very nature of its own location. Okay, let's dive into this. Here is our roadmap for today's explainer. We're going to cover the problem of uncertainty, introduce this idea of the belief state, talk about navigating completely blind, adding imperfect sensors, planning for the unknown, and finally, we'll wrap up with the math of uncertainty. Starting off with Section 1, the problem of uncertainty. And that takes us right into Section 2, enter the belief state and the space of possibilities. Think about a deep-sea submarine, okay? Imagine its cameras have completely failed. Or picture a rover on Mars that suddenly gets caught in a massive dust storm. When the environment just straight up stops feeding you data, how do you keep moving toward your goal without, just crashing headfirst into a wall? Well, to survive the unknown, the AI has to make a huge mental shift. It has to stop asking, "Where am I?" and start asking, "Where could I possibly be?" It does this through what we call a belief state. And a belief state is simply defined as the set of all physical states the agent believes it could possibly be in. So instead of searching through physical locations, like you or I searching through a physical room, the agent searches through a space of belief states. For our totally lost robot, its initial belief state is just everything. It's the set of every single possible physical state in the entire environment. It's basically operating under the assumption, hey, I could literally be anywhere right now. Now, the sheer scale of the math here is honestly fascinating. Let's say an environment has n physical states. For example, imagine a simple grid with just 10 squares. You might think there are 10 belief states, right? No way. There are actually 2 to the power of n possible belief states. So to put that into perspective, for just 10 physical squares, there are 1,024 possible combinations of where the agent actually thinks it might be. It might be calculating, okay, I'm in square 1 or square 2, or maybe I'm in square 3, 5, or 9. The scale of this belief state space just explodes massively, creating this huge complex universe of possibilities that the AI somehow has to manage. All right, Section 3, navigating completely blind, using sensorless searching. So, when an agent is literally flying blind, getting absolutely zero percepts or sensory inputs from the outside world, it leans on a really clever strategy called coercion. Basically, coercion means applying a specific sequence of actions that forces the agent into a specific state, completely regardless of its starting point. Think about it. When you're blind in a dark room, you don't figure out where you are by looking around, right? You figure out where you are by moving and forcing the environment to give you some kind of certainty. To make coercion crystal clear, just picture a totally blind robotic vacuum cleaner in a square room. Its initial belief state is the whole room. It knows it could be on any tile, but if its core programming simply says, hey, keep moving right repeatedly, something kind of magical happens. Even though it can't see a single thing, if it just keeps driving to the right for long enough, it is eventually going to bump hard into that rightmost wall. And suddenly, boom, its belief state shrinks dramatically. No matter where it started in that room, it is now absolutely guaranteed to be somewhere in the rightmost column. It literally forced a certainty right out of the unknown. Okay, so let's see how this evolves when we actually give our AI some tools to work with. We're going to transition from that sensorless search, our blind vacuum repeatedly hitting a wall, to searching with observations. This is where we finally upgrade our robot and give it some much-needed sensors. Section 4, adding imperfect sensors. The moment an agent gets sensors, it starts using them to actively prune or trim down that massive, overwhelming belief state we talked about earlier. But here's the catch.
In partially observable worlds, these sensors almost never give you the full, perfect picture. They provide a filtered view of reality through what we call a percept mask. Think of a percept mask kind of like looking through a keyhole into a room. You can see something, but definitely not everything. For instance, a robotic vacuum might have a dirt sensor underneath it. Through its percept mask, it knows exactly whether the square it's currently sitting on is dirty or clean. But it still has absolutely no idea what its actual GPS coordinates are in the house. It's helpful, sure, but it's a very imperfect, partial observation.
So, how does the AI use that imperfect sensor data? Well, it runs this really elegant internal loop called the three-step update cycle. This is the secret sauce. Step 1 is predict. The AI asks itself, based on the action I just took, how would my current belief state change? Step 2 is observe. The AI receives that new filtered percept from the environment, like, say, sensing a patch of dirt. And finally, step 3 is update. The AI looks at its massive, sprawling list of possible states and simply discards all the physical states that don't match up with the new percept. If it senses dirt, it instantly deletes every single clean square from its belief state. Just like that, the pool of possibilities shrinks. Moving right along to Section 5, planning for the unknown via incremental search. Now, because mapping out every single possible belief state in advance would literally melt a computer's processor, the AI has to rely on a specific structure called a nested and/or search to find a path step by step. It's best to imagine this like a massive branching tree. The or nodes represent the agent's choice of action, like it can choose to go left or it can choose to go right. But then you have the and nodes. These represent the different possible percepts the agent might receive from the environment after it acts. Because the real world is incredibly unpredictable, the agent has to be prepared for this observation and that possible observation. What this tree actually generates is what we call contingency planning. See, the AI isn't just drawing up a single, simple, straight-line path to the goal. It's building an entire if-then logic tree. The plan becomes something like, okay, I'm going to take action A. If I happen to see Percept P1, then I'll do B. But if I happen to see Percept P2 instead, then I'll pivot and do C. It's essentially building this incredibly robust playbook to handle absolutely whatever imperfect observation the environment decides to throw back at it. And that brings us to our final section, Section 6, the math of uncertainty.
So you're probably wondering, how does a computer actually process all of this under the hood? Well, it all boils down to two beautifully elegant mathematical operations on the belief state, which we represent with the lowercase letter b. First up is the predict operation, written as predict BA. This function takes the current belief state B, factors in an action A, and spits out the new set of states that are reachable by taking that action. The second piece is the update operation, written as update BO. This takes the belief state B, factors in an observation O, and returns only the subset of states that actually align with what the robot just observed. By constantly, relentlessly running predict and update back to back, the AI mathematically chops down the fog of the unknown. It's like a 1-2 punch against uncertainty.
And honestly, that brings us to the real core thesis of our explainer today. It's captured perfectly right here, turning uncertainty into a structured mathematical problem. By treating the belief state, which is essentially just a giant, messy cloud of possibilities, as the fundamental unit of its search, the AI doesn't panic when it loses its map. It doesn't freeze. It simply tames the absolute chaos of not knowing where it is by structuring that ignorance into computable, solvable math. It's pretty brilliant when you think about it. All right, I want to leave you with this final thought and question to chew on. If AI can mathematically conquer the unknown through these belief states, what other foggy, real-world problems could we solve next? Think about self-driving cars caught in a sudden, totally blinding blizzard where the cameras are useless. Think about autonomous drones mapping out unlit, collapsed cave systems, or even deep space probes operating light years away with damaged sensors. The exact same principles we covered today, coercion, Percept Masks, and that predict update cycle, those are the exact tools that will allow those machines to survive and genuinely thrive in the dark. Thank you so much for hanging out and exploring the belief state space with me today. Keep questioning the unknown, and I'll catch you in the next explainer.